So for the warm-up, a cannon is 10 feet off the ground. It launches a cannonball straight up with a velocity of 406 feet per second. Imagine that there is no gravity and that the cannonball continues to travel upward with the same velocity. I don't know if we've ever like been shushed before, but that doesn't mean stop for 1 second and then keep going. Okay. Complete the table with the heights of the cannonball at different times. So you had to basically make an expression, and your general setup we talked about yesterday looks something like this. So when we're talking about distance above the ground, your general setup for projectile motion problems will look something like this. Where does the 16 come from? You don't have to overthink it, but when we did the first lesson of this on Tuesday, where did we say that negative 16 comes from when there is what? When there's gravity. So maybe we need to pull up our notes from yesterday. But we'll also review some of those key parts right now. But we saw that they kept squaring the number and then timesing it by 16. Why that happens is because of gravity. So when they say that there is gravity, then you should expect the negative 16 to be in there. So let me pull up the notes from yesterday, or not yesterday, Tuesday. All right, so maybe this will jog some of your memory. We saw that each time they squared the number, then times it by 16. That gives you the distance that it travels. And if you notice with each second, it travels more. Because as it gets closer to the ground, the gravitational pull is greater by a factor of 16. So that we came up with. And then we even saw it represented in different ways. So like Elena's table, she just looked at how much the ball traveled. Diego looked at its distance from the ground. So that's why they have different numbers, but the rate of change was the same. And when I say the same, I mean like from this table to that table. If it traveled 16 meters or feet, then we subtracted 16 from the original height. If it traveled 48 feet, then we subtracted 48 from that current height, and so on. So we saw that it gave something like this. So going back to your notes, I would write down that this part comes from gravity. That this part, which we didn't see in the first part of this lesson on Tuesday, but that would be any sort of velocity. Because if I drop something versus if I launch something, that would affect the rate that it falls, right? And then S stands for, which we did see in the last lesson, S stands for starting height. Not often does it make you make the equation, I will say, but like it might have you interpret the equation. Like it might say, given this function, what was the starting height? And so forth. Now you had to make the equation though this time for the warm-up, so that's a little hard, but now you have a basic setup. Reread the situation. There is no gravity involved, and it was a velocity of 406 feet per second. The cannon is 10 feet off the ground. Relate that to each part, and now make your table of values. And I'll give you 2 minutes with your group. And then I'll do an example with you, but you should be able to do it at a equal values, you kind of need to be able to make the expression, or at least problem solve your way to the answer. So table 5, you'll start us off. Is there going to be a negative 16t squared in my expression? And why not? It's specified, there's no gravity. When it says that, you're not gonna have this term in your expression. So if you did, then remove it. Usually it won't say there is gravity, usually it's assumed, but this one specifically says there's none, so you shouldn't have that term. Table 6, does this problem have a velocity?
Yes.
What is it? So that should be in your expression in front of the t, we multiply it by the t. Because if it's 406 feet per second, how much it traveled would be based on how many seconds passed. And then table 7, do I have a starting height? What is it? That. Okay, yeah, that's okay, I'll get table 7 on it. But here's your expression basically, like you should have done. Or you could have problem solved your way through it. When we plug in 0, because that one was already given to you, into the expression, what's 406 times 0? 0, and then 0% is, and that's my output. Imagine that at 0 seconds is that its maximum height, it's at its starting height. Well, not maximum height, I guess, but it's at its starting height. So there's that. Now you should have filled in the table, and if you didn't, you now have the correct expression. So we need to wait for you to do the calculation, we can't. But table 7, when t is 1, what's my output? All right, so we're doing 1 times 406, which is 406, plus 10 is 417. Okay. Because what I think you did, actually, I'm not quite sure, but double check. Yep. Yes. Or 16. All right, is what this one could be. Because we're plugging in the 1. 1 times 406 is 406. 406 plus 10 is 416. Table 8, what about when t is 2? What's my output? 812. 812. Anyone disagree with that? Cohen? 822, because you have to add the 10, remember? All right, table 9. When t is 3, what's my output? Feel free to use the calculator. So that's the one you guys have. I'll come back to you. Table 1, when t is 4, what's my output? Table 2, when t is 5, what's my output? 2040, and then table 9, when t is 3, what's my output? Would be 406 times 3. And then add 10. Okay, great. Any questions on that? So we're plugging in to that expression, which we made by knowing this fact. All right, this can help you set it up if it ever asks you to set it up. So then our equation to model the distance in feet d of the ball t seconds after it was fired from the cannon, if there's no gravity, is 460 plus 10. In most situations, like we usually problem solve our way through it, right? Like we figure out that it's this. But in this situation, I think you do need the setup. I think it's unreasonable to make you like figure out how they got that. I'll give you the setup, now you just have to memorize the setup. Questions? Okay, so then, did all the groups get to speak? I think I started that. So we'll keep going with where we're at now, but let me briefly read you the goal. So today we're going to be looking at objects launched in the air. So yesterday was when they're dropped, assuming like no velocity. Today there's going to be some velocity in there. You are going to be able to make quadratic functions and graphs to represent the situation. You're going to be able to relate the vertex of a graph and zeros of a function to the situation, and know that the domain of a function can depend on the situation it represents. Really, this is like at least 3 test problems that we're learning today. So please, like if there's any lesson you should pay attention to, maybe do this one. I think it's easy, but of course I'm a little biased, I think it every year, but really you just have to apply what we're talking about. I'm recording right now, I'll link it in the slides. Puzzle piece is lesson 6. You can expect your next quiz to be on Wednesday next week. Over those lessons, and of course you can use your notes on quizzes, so it's not usually tests. Any questions on any of that? Unless you turn something in like yesterday, then your algebra grade is fully up to date. Make sure that you're doing what you need to do as a student. Your job is to come in, do directions, come in, ask questions, all that stuff. But moving forward. So earlier you completed a table that represents the height of a cannonball in feet as a function of time in seconds if there was no gravity. This table shows the actual heights of the ball at different times. So sometimes our actual and our predicted can vary. These are supposedly our actual. Compare the values in this table with those values that you saw earlier. And we're going to make 2 observations. So compare this table on your paper to the one earlier on your paper. Almost like a notice and wonder. Observations are like notices. When you notice about the 2 tables. All right, table 3, can you give me something you noticed about these 2 tables? Okay, the values on this table are less than the y values on the other table. Okay, so that could be one of your observations or one of your notices. So you could say y values less than the other table. Table 4, can you give me another notice? There's 5 x's in both. We'll 0 through 5, but they have the same x's. So, and they even have the same starting amount. They're both starting at 0, 10. So we could put a few things there. We're looking at the same x's. And we have the same starting amount. What's like the math term that we call our starting amount? Where is our starting amount usually on the graph? Y-intercept. So I'm going to use my math vocab on that. But they both start at 0, 10. Okay, so good. Now we're going to plot both sets of data onto the same coordinate plane. Hopefully, we've done that enough times that you know how to do that. I'll show you this one because it's on my screen, and then you guys will add that table from earlier onto your paper. But 0, 10, notice how these are counting. 10 would probably be like really close down here. 1 up 400 would probably be about there. 2 up 758 about here. 3 up 1084 probably around here. 4 up 1378 there. And 5 up 1640. Now you graph the one from the warm up. I'm going to freeze my screen. I'm just practicing graphing coordinates. See if there's anything you notice. Okay, so both sets of data are graphed. Anything we notice about that? And we notice this could be almost like opinions, like there's very few notices you can say that are wrong. And right now I'm opening it up to the whole class and then I'll assign a reporter shortly. But like what type of function do these lines look like that we talked about? One of them is definitely linear. Would it be the blue data or the red data? The blue data. So this one is linear. This one's from my warm up, by the way. Maybe you don't take notes in different colors. But my data from the warm up was linear. Because when I go back and look at the equation, it's in the form y equals mx plus b. It doesn't have a t squared because in that situation, there was no gravity. And when you look at the table, it does increase by the same amount and increases by 460. So that's why it's linear. Can anyone tell what the red data is shaped like? Would you say that it's exponential? Could it be quadratic? Why do they have like actual data? Why isn't it just the warm-up data? What actually happens in the real world when a cannonball is launched? What affects it? Gravity. So this one, even though it's hard to tell, because I mean, you only have some of the data, you can't see that it's U-shaped just from this data alone. But the reason why there is actual data is because actually there is gravity in the real world. So this last part, it says to write an equation for our actual data. I don't think you'll ever have to do that. I don't even think in algebra before. So I'm going to tell you what the equation is, and then we're going to talk about the equation. But this red data is represented by 10 plus 406t minus 16t squared. Okay, that's the equation for the red data. So now that I've shown it to you, what type of function is this? Now that you can see the equation. Is it linear? Is it exponential? Is it quadratic? Yes, because it has a t squared. That's what makes it quadratic. Without it, say there's just a t in there, it's linear. Okay? Questions, comments, concerns? Now this is written in a different order than that formula I gave you. So if we look back at that formula, I told you to write it down. Hopefully you did. You should be able to interpret it. Okay, so we're gonna assign a reporter now. Whoever spoke for your group last, go one to the left of that person. So table 5, what does this 10 represent in this situation? The starting amount, and in this case, it's a starting height specifically. The constant in these problems are going to be a starting height of some sort. Table 6, what does this 406 represent? Velocity, that's the rate that it was launched, which of course would affect when it actually hits the ground, all that stuff. Table 7, what about this negative 16t squared?
Gravity.
That comes from gravity, because in the real world, we actually have gravity. That's why the actual values are different than the ones from earlier. Because the ones from earlier just looked at how it's launched. Okay, good. Any more things? The backside of your paper is going to be kind of like a you try. I think you have all the information you need from me to be able to solve the entire backside, and you have other people in your groups to help you. So going to the back now. You have a new function that represents the height and feet of a cannonball seconds after it leaves the cannon. You're going to evaluate each term just like we did on the page before. You're gonna graph it with your graphing technology. Adjust the window so that you can see it better. You're gonna look at the graph and answer these questions. So what does it tell us about how the cannonball moves? What's my maximum height? When does it happen? When does the ball reach the ground? What domain is appropriate? I'm telling you, this is a bunch of test problems. This is great practice for you. I'm gonna let you try that with your groups. Consider dividing and conquering, consider all trying it and sharing, whatever works for your little team. But I'm gonna give you 4 minutes to start out with before I help you a whole lot. All right, so same reporter as before. I can't remember where I left off. I want to say I left off on table 1 next. I don't know. But what does the 50 mean in terms of the situation? The starting height. So this cannonball started at a height of 50 feet, I think. It doesn't really specify. Oh, it does. Height and feet. Table 2, what about the 312T? Was that table 2? Oh, yeah, it is. Okay. This tells us the velocity was what? Was 312. And the units are feet per second. That's how much it's traveling in feet per second. Then table 3, what does the negative 16t squared tell us? It tells us that gravity is a factor. So that negative 16t squared has to do with gravity. The scientists discovered it a long time ago. So any projectile motion problems, you'll see that in there. It's gravity. Good. Then you had to graph it. Does Desmos read T's? Does it? Ordinarily, it doesn't. I did see earlier that if you do put like D equals, then it knows somehow. But time is usually X anyway. So if Desmos is giving you an error when you type it in, consider changing the T's to X's because I would put time on the X-axis anyway. It also says to adjust the window. How do I do that? What do I press? The little wrench. And of course, if you have your own graphing calculator, you can still adjust the window. You just might have to look up how to do that on your calculator. On Desmos, which you'll have access to for all your unit tests, you press a little wrench and you change these numbers to be what's related in the situation. So we don't care about any negatives when we're talking about real world time and real world height. You won't have any negatives. And this is what it wanted us to change it to. That helps us see it a bit better so that we can answer the rest of the questions. So table 4, what's the graph tell us about the movement? Don't overthink it. How did the cannonball move according to the graph? It went up and then back down. I mean, you could be more specific, but really that's what happened. It started at a certain height, went up, and then it eventually started going back down until it hit the ground. That's why we're not caring about the negatives of this, because you can't have a negative peak or a negative time for this situation. Then table 5, what's the maximum height that the ball reaches? All right, so our maximum height, and like use your logic, would be our highest point on the graph. And can you repeat what you said? Good, so that would be, because it did say estimate, on Desmos, you can click it exactly, so that's kind of nice. And it gives you 2 values. You need to know which is for time and which is for height. Coordinates are always in the order X then Y. Time is almost always X, which means height must be Y. So that answers that. It is a height of 1,571 feet. Table 6, at what time does it reach the maximum height? Perfect. So then we should all be able to answer those types of questions on our expected response, right? There's my maximum height, happens at 9.75 seconds. The maximum height was 1,571 feet. Table 7. When does the ball hit the ground approximately?
50 feet.
Okay, where would my ground be in this picture? Look at my screen.
0.
It would be when the Y is 0, because if this is supposed to be height, when height is 0 is my, I don't know, when it hits the ground. So the x-axis is my ground. Would this one be my answer? Table 7? I'll try to see, let me scroll up. So the x-axis tells us like the ground of our story. Does this one make sense?
Yeah.
Can I have a negative time?
No.
So don't negate that answer. It doesn't make sense because it's negative. Look at my other x-intercept. So it hits the ground at approximately 50 seconds. That's what you said, 50.
Yeah, it's in the ball spot.
So look at it now. Would you still say it hits the ground at about 50 seconds? Let me scroll up since you're back there. It's hard to see. If that's where it hits the ground, it's about what, how many seconds? That's the exact seconds. You could say about 20 seconds, but I'll put the exact seconds because why not? It hits the ground at 19.659. That's how you know. Yeah, 2x intercepts most of the time. You would not include the one that doesn't make sense, you would include the one that doesn't. And this would make sense because it went up and then down, so it hit the ground at that time. Okay? Now, domain, it's asking about the domain, it will ask about the domain on practically every single test. So table 8, domain refers to all the what in a function? All the x's, good. So it's saying what values for the x essentially are appropriate. So table 9, what should my x's start at for this function? 0. Where should they end at? About 25 works. It hit the ground at 20 seconds, so you could go a little bit after that. I wouldn't say too much after that. Going up to like 100 would be too much. Going up to 50 even might be too much. But it definitely would start at 0. You shouldn't have a negative time, and it should end about where it hits the ground. Can it be decimals in between that? Like, can I have 9.5 seconds? So to make this probably something you could recognize on your test, you would say the domain is all real numbers from 0 to 25. So that it includes the decimals, which it does. You can't have a decimal of a time, a second. But you can't have any negatives. That's why we're specifying from 0 to 25. Good, any questions? That's really it. That's the whole lesson. You have a good chunk of time to work on your practice. But also there is a lesson synthesis. I'll provide you the answers to that later in case you're interested in giving that a shot or interpreting the expression. But we do also have a practice to work on. So please use this time wisely. Adriana.